I guess Mayank, you can just go ahead and start whenever you want.
Yeah. So let's now. Uh, mm, so we have to start from uh, the heading handling long sequences. And I think we should cover to the end of this chapter because the text is. Uh, I looked at the code, and yeah, that is much more interesting as compared to the text here. So yeah, we can, I think so, cover and end the chapter here. And maybe next time we can look at the exercises or the code because that's interesting too.
Great.
Yeah. So let me put in. So are you typing in the chat too?
I am. Yeah, I'm just typing about this new study group.
Okay.
The neat thing about Jan LeCun's course is he does spend time on linear algebra. That's one of the things that is lacking in understanding neural networks is a lot of linear algebra.
Hmm. Yep. Because in the end, those non-linearities are being applied to those basic functions. And if we do not understand those basics very well, so in the high dimensional case, with the affine transformations and all, it becomes very hard to keep up.
Absolutely.
You should check out Gilbert Strang's course. Has all the linear algebra that you need. And I think the 2020 version, he has a mini series of 6 videos. It gives you a good overview.
Which course is that?
Gilbert Strang's linear algebra.
Oh, Gilbert Strang.
Raquel, can you share the link to that one?
Yeah, sure. And I think even in the course that the NYU course, I think Alfredo does reference that too. Let me share the link.
Cool. So, if anybody else has anything to add, or we can start in minutes time.
Yeah.
Good. So let me set the timer up. Share this. So we will reconvene after this timer ends. Hey there. So, what's up with the reading part? I hope you guys have reached to the end, or would you like to have extra 5 minutes?
Yeah, extra 5 minutes would be good.
Oh, cool. So let's start. Guys, can you hear me?
Yes, all systems go.
Okay, good. So last time we looked at the basics of the RNNs and how the uh, simple RNN layer is being used. Yeah, we had a deep network of three layers with the two simple RNN layer, and the third one was a dense layer that was wrapped around the time distributed Keras layer. And we saw that how the last uh, uh, MSE with respect to the deep RNNs are able to perform better as compared to a single celled uh, or the single layered RNN. So now we will go into uh, the topic of handling longer sequences. So here the author has uh, asked us to train the RNN on a long sequence that makes the kind of problems that are associated with the RNNs in a very deep network, very complicated, uh, due to the unstability of the gradients. Uh, there are two issues, and they may explode, uh, as in since the activation function that we use is tanh, and uh, it is bounded between -1 to 1. So it may explode as in all the outputs from a particular gate may reside uh, in the area that's the maximum, that's the upper bound here, that's the one, or the vanishing gradient problem, in which all your uh, how do I say it? Those proper signals that we achieve from the previous inputs, that all kind of vanish, which you can say does not carry over because uh, this is a long sequence. So that's the two issues that we have to solve. And in the next paragraph, fighting the unstable gradients problem, the author has given some tricks with respect to good parameter initialization. That's the bootstrapping uh, with respect to what the initial uh, values that we can give. The faster optimizers, the dropouts are in the sense of RELUs and so on. So these are the steps. And next, with respect to those non-saturating activation functions, uh, with here, like RELUs may not help because it may uh, even cause them to be unstable at RNN, to be unstable during training. So why is that? Suppose the gradient descent updates the weight in a way that the output slide that outputs slightly the first time step. And because the same weights are used at every time step, the output at the second time step may also slightly increase. And those at the third, and so on until the output explodes. So that's the kind of a non-saturating activation function, uh, uh, which does not prevent that. Yeah, it may remove some of the parameters that or or the variables that are taken into account, but it won't prevent it from uh, ex, exploding the gradients in a sense. We can, of course, reduce this by using a smaller learning rate, but this saturating activation function, like the hyperbolic tanh, the tangent that we use, uh, it that's why it's the default in the simple RNN layer, and it's the default for the GRUs and the LSTM cells too. Uh, the next, the author has given an advice as to if the training is unstable, then the then he has told us to monitor the size of the gradients using the tensor board or use gradient clipping with respect to the initial uh, the back propagation that's happening, the both for the forward as well as the backward passes. Then in the next paragraph, the batch normalization cannot be used with RNNs, and it's because uh, you cannot use it between the time steps, only between the recurrent layers. And there is a code example as to why this is being used. And at each time step, intuitively author has defined that uh, since it has to be applied at each time step, both on the input that time step and on the hidden state from the previous time step, so it will cause a kind of uh, scaling and offset of the inputs and the hidden state. So that would be kind of harmful. Uh, yep, it looks good in the intuitive sense because uh, we are all are go for regularization and normalization at every step. Uh, but in practice, it doesn't because uh, uh, when applied to the inputs, it only gives positive results, not in the hidden state. So that's why, and they have done it in Keras by adding a simple batch normalization layer, which before each recurrent layer. That's one form of it, and there is a short snippet of code in the Jupyter notebook that is associated with this chapter, in which the author has given a kind of an example with respect to adding. If I can quickly show that here. Um, Batch norm. Yeah. So here, after each simple RNN, batch normalization layer is being applied. So this is the way author has represented it. And so next form of normalization that works better to offset this issue, we had layer normalization. it is very similar, but instead of normalizing across the batch dimensions, it normalizes across the featured dimensions. And the advantage of that is that it can compute the required statistics on the fly at each time step independently of each instance. Uh, this behaves the same way during training and the validation phase as opposed to the batch normalization. It does not need to use the exponential moving averages to estimate the feature statistics across all the instances in the training. So this is like the batch norm, layer normalization scales, and the offset parameter for each input.
Question, Mike,
Yeah.
what does he
Mhm.
mean by it's different from batch norm because it's batch norm has to do something different in training and testing?
Here, with respect to batch norm, they were calculating those gradients, those normalization gradients across the batch.
Right, but why does it say it's as opposed to BN, which is different, or what does he mean there that BN is different during training and testing?
Here, with respect to the validation phase, when you have that, because I think so intuitively, what the author means is since this is a simple RNN layer that is being applied across 20 units, then it is being batch normalized here. So here it works fine, and then the 20 units, and then this right here. But if we try to apply this between the layers, I mean, suppose in these sequential models, we have those gradients that are flowing. And if we try to apply it between a sequence of in inputs, then it does not kind of goes very well practically. The empirical evidence is, how do I say it, a bit negative here. So,
Right. So between layers you don't use, but what I didn't get is, or what I forget when in usage of batch norm
Srinivas,
is
for batch norm during training, you use a batch, right?
right.
Whereas at test or inference, you don't necessarily need to have a batch. So then if you try to calculate for a single image mean and variance, you'll screw things up. So that's why I
Right. So
used
which
to
is why
use
you do the thing he's
running
talking about
stats.
of calculating the running average.
Exactly. That's what. So you basically set running stats is equal to true. So you basically use that at inference.
Right.
Now, when you
So
come down to layer, there is no necessity of that, right? Because you're not doing it across the batch. You're doing just for each feature map. So
okay.
that's
So
where
that's the difference between
on the
that.
fly, yeah. And irrespective of it being one image, two image, three images, you can still calculate it during training, during inference. It's just, I mean,
Okay.
doesn't
Got
affect.
it. Yeah. Thanks.
yep. Yep. Here also, you can see there is a custom LN simple RNN cell in which the author has used layer normalization. That's the same example here. This example, yeah, the author has. This is the code for it. It's I think actually the same. Get initial states and called. Yeah. Uh,
So what does that mean to normalize across the features dimension? The features are like if you have a sentence as an input, the features are the individual words to the sentence. I'm not quite sure what he means by that.
Features are with respect to those inside those particular layers, those deep uh, units. So if we look at, yeah, here, so inside each cell, those features that are represented. So if there is a particular element we have suppose HELLO, and then we had the output of we had the problem of predicting the next letter in the sequence. So those features that represents the weights of a particular layer that's inside a deep RNN. So here, each cell
Okay.
that
Okay,
yeah.
so it's either the input itself or the transformed version, the weights related to that input down in a deeper layer, in a
Yes.
deeper level, I guess.
Yes. So,
But it's horizontally. It's normalizing horizontally across. Is that?
no, I think so. It's normalizing vertically across because these are the deep features. So yeah, at each level, those inputs will be. That's it. I didn't.
Yeah, I think it's right. It's vertically, right? Horizontally will be the time step axis, and we just said that it's hard to do that. Doesn't make sense to do that, so it has to be vertically.
Yes.
No, but vertically means if you suppose you eliminate the multiple LSTM and just go with one, then across what dimension would be my question.
It'll be just after the first output, right? So if you look at the code, if you scroll up, oh, sorry, no. Oh yeah, that's with batch norm. But yeah, you can see the same thing there also, right? It's after just that first RNN. So that'll be after just that first vertical step. If you were to look at whichever that figure is on the left-hand side that Mayank is predicting. At least that's what my understanding is.
Yeah, but if you don't have multiple layered LSTM.
The difference is batch norm is placed between the RNN layers, but you can place a layer norm between each step. So normalization is done after the cell produces its output. And can we go to the code there?
So you're saying horizontally. You're saying
horizontally. Yeah, I mean it would be normalized between horizontally, right? Between each time step.
Yeah, and across the edges, let's say edge is 300. It's across the edges 300 values. Is that right?
No, it's done across the last dimension. So it would be done across the like if our sample is in shape of batch size, then time step, and then like our feature dimension, number of hidden units. So we would calculate mean and standard deviation for each for last channel, for this hidden dimension channel.
Yeah, so if the hidden dimension is 300 wide, it would do it across those 300 dimensions. Is that correct?
Yeah, right. Here we have 20 and
yeah. Whatever the hidden dimension is across that.
So yeah, here it's 20. Yeah.
Is that right? No, it's
if you look at the code, the hidden dimension for RNN cell is 20. We have 20 hidden units. So we calculate mean and variance across
those 20.
Those 20 units.
Yeah.
And
right.
So it would be like mean of the layer, that's why it's called
exactly. It would be between these yellow rectangles, like where the arrow going right is, it would be just at that intersection, and because that's the output cell, and you would do it across the 20 outputs that goes from the first orangish block to the next orangest block. Forget that stacking vertically. Just assume only one stack exists.
Isn't it both? If you go back to the code on the left-hand side, on the PDF, you scroll back up where he's created. I think you already jumped it, right?
Handling long sequences. This is the simple RNNs. These are
LN
the
simple RNN cell. That's the one we're looking for.
And then
I think you have to go back up.
simple RNN cell.
Which figure is that, sorry?
This figure was 15-7. 15-7.
Oh, so it's after 15-7.
So this is the code. But here.
No, not this one, sorry. Why the hell can't I find it?
With respect to the batch normalization, I don't think so. The code is there in
No, not the batch normalization. This is for the LN.
LN, okay. LN simple RNN cell?
Yes.
Okay.
Yeah, so here, if you, I think the one you have pulled up, right? So if you look at the call, you calculate, you pass this through your simple RNN cell, you get your outputs. This is what is being passed through self.layer norm, right? And so this norm outputs in this case of simple RNN cell is both top and right? If you look at the figure.
Yeah.
Or am I
that would make sense, Rekil, because the output is being sent upwards and rightwards.
Right.
So that's why I keep saying, forget about the upwards for a minute.
Okay.
Right. Then it is between the layers, because let's just assume a single, instead of stacking RNNs, let's just assume first solve the simple case of unstack just a single vertical layered RNN, and then it's on the right. But that same output goes to the top. So therefore it's both. But as Arto just said, the important thing, even in a single case, is it's the output. That means it's across the 20 hidden dimensions.
Right. Okay.
So let's use a TF. So here, the author has created a class ln simple RNN cell, and we need to define a custom memory cell with respect to call, and this is for the layer normalization, because it learns the scale and the offset parameter for each input that has been provided. So it does it. So layer normalization can be applied both ways. That's why. And on the right, it's just being applied right after the simple RNN cell layer. So here the layer normalization is being applied, and plus I think so the layer norm is also being applied here with respect to the outputs of each and every cell.
So I think what happens is a simple RNN with no activation, all it does is combines, it's just a linear layer that combines the input with the hidden layer. And the layer norm is being applied right there, where right after the linear combination between the input and the hidden layer is formed, and before the activation. So it's inside that, little yellow rectangle. As soon as the input enters from below and the hidden state enters from the left, then inside that yellow inside that yellow rectangle, that's where the layer norm happens, and it happens across, in every one of those yellow cells.
So here and then here across this two.
Yeah, and then across each layer in turn.
Yes. That's the difference between layer norm and.
So you have to have a special simple RNN that has no activation. They're doing it in a custom code there, that because they want to get inside the RNN before the activation is applied. So that's where the layer norm is applied. And then they apply the activation by hand afterwards.
Yes. So that's what has been described here inside this whole paragraph. And then they have stacked these ln simple RNN cells.
Sorry, Mike, one more question, because I haven't run this yet. Is this norm outputs and the list just the current output and then the list of all? Is that what that last line is?
Now finally it returns the output twice. Yes.
It's just the current and then the list, which is the entire sequence. Is that what that line represents? I forget now. So
this
I think
line?
one is the hidden state and the other is the output, but they are the same in RNN, right?
yeah, so it's the hidden and the output, but is this a list because it contains multiple?
No, I think this contains just single one. It won't contain multiple instances.
So why is there a listing in one case and not in the other?
That's a good question. I don't know.
Yeah, he says later on to ignore the second one because it's the same as the first one.
Yeah, he references that as norm outputs of 0, right?
Yeah.
New states 0.
Yeah, but then norm outputs would be a sequence, right? If you're slicing it.
I think like in LSTM, it'll be like C of t and H of t sort of a thing, at least my understanding.
No, it won't be. It can't be different if you slice. It has to be, anyway, that's fine. I'll run it and look at it. But I was just curious, why is one a list and the other, if it's the same, is it the sequence? But that's fine. I'll have to run it and figure it out.
So
okay.
Yeah, that's a good
connected
question.
With internals, how the RNN layer is implemented. So it's further used in this RNN layer, and probably you can like for LSTM we have two hidden states, like two this C, and
yeah, H and C, right?
And maybe just RNN layer in Keras expects it to be in a list because you can have multiple hidden state vectors.
Okay, thanks.
Yep. If Just my intuitive understanding, if I look at this figure again, so we have two. One is a single value, and the other is a list. So you can think of the list as being applied here. Each of the units that is being propagated upwards. Maybe that's the input to the next layer that is being given from simple RNN cell, and the single norm outputs. The singular value is being forwarded from left to right, as in the HT.
Right. Okay. So does this kind of relate to with when you set return sequence is equal to true, whereas norm outputs without the list is just going to give you the last output, whereas norm
Yes.
output in the list will give you all of them?
Yes, I believe so. But yeah, I will still have to
Cool. Okay.
confirm my theory, but I believe that this is how it should work. So, forward. So here we are, yeah, that's the thing with respect to the return sequences. Uh, why we have had true here, the Boolean value of true, yeah, with respect to the sequences, uh, those time distributed wrapper that's around the tens layer. So, and so similarly, the author has told us to create a custom cell to apply dropout between each time steps. Uh, but there's a simpler way. All recurrent layers except for keras.layers.rnn and all cells provided by the keras have a dropout hyperparameter and a recurrent dropout hyperparameter. And the former defines the dropout rate to apply to the inputs at each time step, and the latter defines a dropout rate for the hidden states also at each time step. So there is no need to create a custom cell to apply dropouts at each time in the RNN. So that's the two hyperparameters that we have. This can elevate the unstable gradients problem. Uh, this can help train the RNNs much more efficiently. We have to look at the short-term memory problem. So, due to the transformations that the data goes through when traversing an RNN, some information is lost at each time step. After a while, the RNN state contains virtually no trace of the first inputs. Uh, as I have alluded to earlier, and this can be a showstopper. This is a simple example of Dory the fish that's trying to translate a long sentence. And by the time she is finished reading it, she has no clue how it started. This is to tackle this, a long-term memory has been introduced. It was successful, so basic cells are not being used anymore. So let's look at this popular LSTM cell. Uh, so this was proposed by Chef Horst. Yeah, I'm butchering their names, but Jürgen Schumpeter gradually improved over the years by several researchers, and they provided some variation of their own implementations. There are some nested LSTM stacks too. Uh, I looked at it once, uh, but we considered a normal vanilla LSTM cell, uh, and as a black box, it can be used very much like a basic cell, except it will perform much better. Convergence will be faster and will detect the long-term dependencies in the data. In Keras, we have a LSTM layer. This is the keras.layers.lstm. Uh, so we have replaced that with simple RNN, and it will work just fine. And what we can do is we can have a wrapper around in a class that is a RNN class, keras.layer.rnn class, and keras.layers.lstm cell is the cell that is being used. So here the 20 cells are being used, and it will produce the same uh, uh, formulation or the architecture of the RNN that we are trying to build. And now we go to the optimized implementations when running on a GPU. So, yep, and this is with respect to the Keras implementation, which uses CUDA. So it's generally preferable to use it. Uh, RNN cells is mostly useful when you define the custom cells. So we have to use LSTM layer as opposed to this implementation. This is referentiable LSTM layers. And now we go into the inside of LSTM cells and its architecture. So it just looks like a regular cell, except that its state is split into two vectors, h of t, which is coming in from the previous time step, and a c, where c from the previous time step stands for the cell. So h of t is a short-term state, and the c of t is a long-term state that is being propagated throughout this cell. So, and to give an overview of the symbols, this is the element-wise multiplication cross, and this is the addition, and this is the logistic and the tanh activation that is being applied to the fully connected layers at each these four uh, layers. So 1, 2, 3, 4. Here's the input that is being received. So sorry, x of t is the input, h of t is the short-term state, and the c of t is the long-term state that is being given. And the combination of h of t minus 1 and xt is being fed into the fully connected layers of these four layers, these four, you can say gates. Yep, that's the correct terminology. And so if we go inside this box, um, uh, it's kind of cool. Uh, the key idea is how the network learns to store in the long-term state and watch and what it throws away and what it reads from it. So, and as the long-term state CT minus one traverses the network from left to right, you can see that it first goes to the forget gate. Yep. And it drops some memories here. Uh, and there is an input from uh, here too. This because it is being multiplied by this forget gate. F of t is the forget gate here. And then it moves forward to the addition. And here the memories that were selected by this input gate. So here you can this crosses the input gate, and uh, these are some of the selected memories that are being added to the performed. The iterative refinement is being performed here, and then the results of this CT is being sent straight out. So without any further transformations. So at each time step, so this whole cell is one time step. So at each time step, some memories are dropped and some are gained or added. So that's the whole how do I say it work of this CT. That's the long-term memory. So this also passes through this tanh function too. It has a result that is being filtered by this O of t, which is the output gate. It produces this guy H of t, which is being which is the short-term memory, which is equal to the cell's output for this time step. So this is being propagated forward. And if I go to the depths of this, first the current input vector x of t and the previous short-term state h of t minus 1 has been fed to four different fully connected layers. So these are the four different layers, and they all serve different purposes. the main layer is this guy here, which has the tanh activation, and it has the usual role of analyzing the current inputs and the previous states. And this is the main because uh, the output goes straight from, if we compare this to the vanilla cell. So this is the main because the output goes straight to this to the next state. And in contrast, here in the LSTM, it does not go straight out, but these are the paths that it goes through. So this is the dropping point with respect to this main gate and the input gate. So I call it the gate. It's a GG because there's no uh, no, I didn't find any uh, easy term for it in the literature. So uh, it's taken from the Justin Johnson's talk which he gave. Uh, uh, then the other three controllers, the forget gate, input gate, and the output gate, they use the logistic activation functions, and their output range from 0 to 1. And uh, as we can see, all of these outputs are being fed into the multiplicative operations for the forget gate here, for the input gate here, for the output gate here. So this is it. And so this, what it does is that the outputs are fed to the element-wise multiplication operations. So if they output zeros, they close the gate, and if they output ones, they open it. So that's the whole raison d'etre of all these three gates. The forget gate that is controlled by FT controls which part of the long-term state should be erased. The input gate that is controlled by I of t controls which part of GT should be added to the long-term state here. So this is the main controlling factor here. And finally, the output gate that is O of t. Yeah, here it has the control of which parts of the long-term state should be read and output at this time step. That is both ht, both to the h of t and y of t. So this is the thing here. So in short, we can learn to recognize the important inputs by this input gate. The second is store it in a long-term state by this main guy here. Preserve it as long as it's needed. Uh, that's the role of the forget gate, and extract it whenever it is needed. So that's the role of the output gate. So these four are the main pointers intuitively, which we can understand from these four gates. These explain why have they been so successful in capturing the long-term patterns in the time series, long text, audio recordings, and more. These are the equations with respect to these, which are very simple here. Yeah, here I of t, which is followed by this logistic activation function, sigma, w of xi. So xi and whatever the w of x and those any number. So we can think of it as the weights that are coming in from the bottom. So bottom up. So these are the weights that are being applied in the context of w of x, and the weights that are coming in from the right to the left as we have seen here, let me get back to this figure. Yeah. So just let me. Yeah. So W of W here of H, W of I, and whatever the number here is. Not wrong. So these are the weights that are being applied here. So we can think of it as this. Right. Yeah, W of X and W of H. Sorry. Yeah. So W of X is from the bottom and W of H is from the left. Yeah. This is for the ith gate. And for F, this is for the F gate, for the Oth gate. And yeah, these are just simple matrices that are being manipulated. Yeah. So, and the activations that are being applied here, it's the logistic sigmoid, and here it's the tanh. That's the main part, and C of t and Y of t is here the combination of these four gates, and the Y of t is the output that we get here. So these are the six equations. So here in the bottom, they have defined which these weight matrices of the four layers in connection to the input vector x of t, and weight matrices with respect to the four layers in connection to the previous short-term states, and then b of I, b of f, b of o, and b of g are the biases terms for each of these four layers. And the bootstrapping here for the TensorFlow is vector of poles of ones instead of zeros, because it prevents the forgetting everything at the beginning of training. So this is very important, as alluded to earlier, with respect to the bootstrapping process that it utilizes. So that's it here. Then comes a peephole connection, and the people connection, what they are doing is they have a LSTM variant with an extra connection. And what they are doing is uh, the previous long-term state, C of t minus 1, is added as an input to the controllers of the forget gate and the input gate. Uh, and the current long-term state, C of t, is added as an input to the controller of the output gate. So visually, if we want to see this guy here, yeah. So here, what they have doing is people. Yeah, this is the tag diagram. So if we look at the text here, the previous long-term state C of t minus 1 here is being added as input to the controllers of the forget gate. So this is the forget gate. So here is being inputted here, and the input gate. So here is the input gate. So this and this guy is being added here, and the current long-term state C of t. So here is the C of t that we receive after this C of t tilde, or the uh, G of or the G of t, as we call in this book. It's being propagated to this output gate. So That's it. That's the whole thing. It's just a seems like a peephole connection. That's the term. Uh, there is an experimental peephole LSTM cell that does it. But you can also create a RNN layer and pass the peephole LSTM cell to its constructor to uh, get the same kind of architecture. But I don't think so that this will work with respect to the parallelization in the GPUs. Even I have a confusion with respect to those. Does this experimental peephole LSTM cell supports? Yeah, the GPU parallelization. Yeah, and that's an open question. Maybe I will explore it further. The next is the GRU cells. So here, what they are doing is uh, it's kind of encoder decoder architecture. So that's why we do not have the C of T. That's the uh, layer that we had earlier. So yeah, I think so. The code for that is the custom RNN classes. So it's a simple call function, then the zeros and the right. LNM. So this is a simple LSTMs as we looked at. This is the evaluation, the curves. This is with respect to the multiple forecast, and we are coming into the GRU part, which keras.layers.gru is being provided here. So if we look at it from this perspective, this cell is a simplified version of the LSTM cell, and it performs just as well. Here, the both state vectors are merged into a single vector h of t. Uh, what we mean by that, it is the this is an update gate here. So this R of t and a Z of t inputs are being merged here to a single vector h of t. I hope I'm right. Single gate controller Z of t. Yeah, this guy here controls both the forget gate and the input gate. Okay, so this controls both the forget gate. Okay, yep, and the input gate. And if the gate controller outputs a 1, the forget gate is open. And if the input gate is closed, yeah, this guy here, 1 minus, it outputs a 0 and the opposite happens. So yeah, this output has been split twice here into two directions, and this happens.
So question there, like how do we name those three gates here in this figure? Like it can't still place which one is supposed to be which.
Yeah, this figure I have a bit of a confusion. So I understood it by this guy here. This is an LSTM. These are GRUs.
What I understood is the G is what he calls the input gate or the main gate, and then I think the Z is the forget gate. I think, but yeah, there is a little confusion because he talks about naming these gates, but he doesn't connect the names to the letters.
Yeah, best to go to the 224 diagrams for the interpretation records.
Okay.
That or the Cola blog or the best.
Sounds good.
Yep. And then these are the computations with respect to the Z of t, R of t, G of t, and the H of t. Since this is an encoder decoder, since yeah, we have just got the H of t that is to be taken care of. And then they give a difference between the LSTM and the GRU cells and the simple RNNs and why they have come so far with respect to handling the audio samples, the long time series, or the long sentences. So this is it from this end. Even I have a bit of a yeah, quandary here with respect to the naming convention that everyone has used here. But next is the using 1D convolution layers to process sequences. Here, what they have done is replaced that how do I say it? As a additive in argumentation or to lower the compute requirements. And what they have done is added this 1D convolution layer at the top. So if we that that can slide several kernels across a sequence that produces a 1D feature map per kernel, as we have looked at previously in the CNNs. So that's what is happening here. And if we look at the kernel level architecture, the how kernels work in a CNN, it will learn to detect a single very short sequential pattern that's no longer than the kernel size. So if we use 10 kernels, then the layers output will be composed of 10 one-dimensional sequences that are of the same length. And you can view this output as a single 10-dimensional sequence too. So yeah, this helps in, how do I say, dilation and yeah, those convolutions as we have known uh, in the literature. So this intuitively also means that we can build a neural network that's composed of a mix of recurrent layers and the 1D convolution layers or even the 1D pooling layers. So yeah, and if we use a 1D convolutional layer with a stride of 1 and the same padding, then the output sequence will have a same length as the input sequence. But yeah, this is the with respect to the padding and the stride that is greater than 1, it will be shorter. So you have to adjust targets accordingly, yada yada, as we have seen previously. So, following the model in the same as earlier, except it starts with a 1D convolutional layer that downsamples the input sequence by a factor of 2 using a stride of 2. So here, the kernel size is 4, the strides is 2, it's downsampling it. The kernel size here, it's larger than the stride, so the inputs that we use to compute the layers output. Therefore, the models can learn to preserve the useful information, to dropping only the unimportant details. Yeah, by shortening the sequence, the convolution layer may help the GRU layers detect longer patterns. Yep. And we may crop the first 3 time steps in a target since the kernel size is 4. Yeah. And the output of the convolution layer will be based on an input time steps of 0 to 3 and a downsampling the targets by a factor of 2. Yep. So at the first layer, those 3 inputs, 0 to 3 at first can be cropped off because the kernel size is 4. So it is being downsampled here and then being utilized. So those features will be here, as we have seen earlier. So and then the compile and the fit, and this will perform the best because it's and Jaron also points out that it is actually possible to use the fully 1D convolution layers and drop the recurrent layers entirely too. Let's look at the code for this one. This is must be, yeah. This is a 1D convolution layer with a kernel size of 4, stride 2, valid padding. So at the 0 time step, this is the kernel that's been taken at the 1. This is the X in input. This is the output. That's why, yeah, these are the time step and the kernels that are being. Uh, the output will be 0 here, 3. 4, 13. 2, 5. Yeah, as we can see here. So 6, 15. Yeah, 2, 5. Okay. 6, 15. Okay, on the second time, the first time producer, it will be 6. Okay, 15. Okay. And on the third will be 4, 7. 4, 7. Yeah, so this is the sequence that can be taken care of. So this is the code for it, and the model is fitted in the Y training that's between 3 colon. The second dimension is from this guy to this guy here. So that's the only difference between the previous mm, uh, training and this data that is being inputted. So in the end, this will perform the best. So this will have a loss of 0.18 of 0.018. Sorry, that's the best as compared to all the other approaches that we have seen so far. So now coming on to the next, the last section of that's the WaveNet. Here, DeepMind researchers introduced WaveNet, and what they did is, let me give a quick, this guy here. So this is the WaveNet blog. Let me try to share this. So as you can see from this figure, it's kind of like self-explanatory. So the architecture that they have taken is from the Pixel RNN and the Pixel CNN models. And what they have done is applied these convolutional layers totally with the stacked here in the diagram, the architectural diagram, as you can see in this animation below. Yeah. What they have done is the input, then the convolution layer of dilation 1, and then the convolution 1D of dilation 2, then the convolution 1D of dilation 4, then the convolution 1D of dilation 8. So at each time step, the inputs that they have taken in are being halved. So yeah, it's kind of like simple, intuitively understand it. So this is the simple explanation. Uh, so this is with respect to the this also affects the receptive field. So how many neurons, how many cells to be exact, it has to take into account at each of the uh, time step as we as it goes higher from the bottom to the that's the input to the output. Uh, there are a couple of cool concepts too, which has been introduced in this alongside it, but yeah, this is the main thing, and then this is for the con 1D filter with this varying dilation rates, and the padding is causal. Why causal? Because yeah, it's been uh, intuitively kind of like how do I say it? Uh, uh, it does not allows this uh, this causal padding does not allow this layer to peek into the future when making predictions. So uh, uh, with the right amount of zeros on the left and using a valid padding kind of. So it does not goes too further away and stays in its own boundary. So that's the reason here. The causal padding is being used. Uh, Other than that, uh, it's a simple architecture. Uh, we have added here a similar pair of layers using the growing dilation rates and the 10 filters of size 1 without any activation functions. So here on the second layer and the fine so this is fully with respect to the con 1D as a pair as opposed to having any RNN layer or any cells.
Then at the end, there's a 10 unit, there's a conv layer with a one-dimensional convolution, and I think it's producing a linear combination of the outputs of the 10 layers at different scales. I think that's what that final output layer is doing. Anybody have any different take on it?
Yeah, I guess uh, this is the yeah, I think so too because those con 1D at the filters 10, the kernel size of 1, what it is doing is uh, those special dimensions as we have seen in this figure. Yeah, those I think so. Those are being compressed down to a single point. So these are the 10 outputs that we have. Let me see if there is any other quick explanation with respect to. paper, because in the paper, yeah, I had opened this paper. Yeah, this was the paper. So in the paper they have applied the softmax in the architecture, but in the residual block and the entire architecture in which they are using the skip connections. Oh, with respect to that, what the implementational tricks are, I am not bit clear on that, but
It looks like that's what's happening. But yeah, so we can think about that. But I have another question. In the code block for the implementation, which is right under figure 15.11, if you have your
50.
It's right under the figure 15-11. Yeah, that code block. And if you're looking in your book, it's page 522. There's that for statement. I'm not quite sure what, I think I know what it means, but I'm not quite sure. Does that mean it's executing 2 for blocks in a row? That's what that ×2 means at the end? Does that actually mean 2 for blocks?
That's just 1, 2, 4, 8, 1, 2, 4, 8. You just have a list of 1, 2, 4, 8, 1, 2, 4, 8.
Okay.
So your for is just running through 8 elements. 1, 2, 4, 8, 1, 2, 4, 8.
Okay. So it's actually creating 2 sequences of spatial, 2 sequences of dilated convolutions that are followed one on top of the other.
I think it's just doing one set of dilated convolutions of 1, 2, 4, 8, and then following up with another set of them 1, 2, 4, 8.
Yes, but each output gets added on top. I mean, the whole thing, the 8 things happen in series.
Yes, that's what I also think.
So
yes.
yeah, so it's
happening
the
in
same.
series.
Yeah, so it's the same as 2 of the 1, 2, 4, 8 blocks in a row or something like that. I mean,
Yeah, if we could have just written for rate in 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8.
okay, I just wasn't sure about how to interpret that ×2, whether it meant to multiply everything inside the tuple by 2, but it apparently doesn't, right?
It's repeating it, yeah.
It means repeat the tuple, yeah.
Yeah.
Okay.
Yeah, it's similarly defined here in the dilation rate and the to the power I for I in range. This guy here, number of layers per block multiplied by the number of blocks. So this.
Oh.
So here we can add or remove the number of dynamically and instead of hard coding it. Yeah. And the other thing is they have used a gated activation unit, which I don't think so. We have it in the book. That's the other interesting, intriguing thing about this wave networks. And which just it's a simple activation with respect to those damage. And
Yeah, kind of brings in like the RNN, the residual nets, there are a bunch of things that WaveNet kind of combines. But their simplicity purely is that it's 1D convs. And as you keep increasing stride, you kind of like exponentially start seeing more in the past, which is what kind of helped with the audio generation and kind of making it more natural.
This is related to the Rekil, this is related to the object detection problem that you guys were working on in Kaggle, right? where you had dilated convolutions, except they were two-dimensional.
Right. I mean, so the concept with the dilated convolution is you kind of start seeing more than what if you would have seen at a smaller rate. So if you, like you said, you see a lot more when the dilation rates increase in terms of, like you were talking about object detection or semantic segmentation. There you need more of the context. You just don't want to be zoned into small things. Here it's kind of the same concept, but here it's that a word which was said longer time back, it'll kind of get lost if you don't have strides equal to 2. Because the only other solution if you don't have strides equal to 2 is you need to put those many more conv layers stacked up. So then you increase compute by that. Instead of having just 4 conv layers, you'll have like 8 conv layers. So the trick to get around that is that you increase dilation rate. So now you're still seeing that much more behind, but your convs are just going to be 4 convs instead of those 8 convs.
It's like receptive field
increased, yeah,
becoming larger. As you see for the blue thing on top, it goes all the way to the green, starting at the 4th, and all the way to the current input. So, but what is this thing about looking into the future? I didn't quite completely grasp that. He says it prevents the convolution from looking into the future. I mean, I can intuitively understand what they are trying to prevent, but how does that happen in this case? Because you're looking past all the time. So where or what am I missing?
I think that's the leftward padding that happens, so that you only pad to the left, which is in the past. So you don't get to see any of the data from the future. I think that's all it is.
I think so. Yeah, and this if we look at this too, this animation, yeah. So it's with respect to those areas that have to be covered by particular those sliding windows, as you can see, or as Joseph just pointed out. Yeah, that's
so. So Joseph, you're saying that because of the padding, you're preventing it from stepping ahead and therefore looking at things, because you, by padding and making it look to the end of the pad, you're still ensuring that it doesn't move forward.
I think
and
so.
Look at
Yeah.
the future.
Yeah, like for the hint, like if you look at that diagram, the animation that's showing, every level is passed on, but it's padded from the left to make it long enough, and so nothing from the future that anybody hasn't seen is included. Any of these levels haven't seen. Nothing that any of these levels haven't seen from the future is included.
Allowed.
Yeah.
Okay.
I think, yeah, the other difference here is like, isn't this convolution that is happening here kind of not the traditional ones that we have seen where you kind of center on a pixel and then you see future and past and like pick out, like if it's a 3x3 kernel, you take one from back, one from front, one from top, one from bottom. Whereas in this case, it's the causal part of it. That's what my understanding also is, that it's just looking backwards, and what we're padding is like you're kind of balancing it out on that side.
Yeah.
But yeah, I mean, it's kind of, if you look at that diagram, you wonder when would you ever be looking into the future? So
that was my,
that's a valid question. Yeah.
Yeah, but with respect to causal, padding, I agree too. Yeah, there is some different viewpoints that can be. I think so. This figure does not give this query justice, but yeah, we might have to look further into this. So, any more queries, discussions? Because this is the end of this chapter. And there, I will like to point out that there are some cool implementations that are there with respect to this sketch RNN datasets I tried it. I haven't still gotten to the full understanding and experimentation and the playful part yet, but this looks interesting. And maybe the author has also suggested to try different layers and different cells as to see how it performs. This looks interesting. So, and the batch with respect to the songs that it has generated, these looks great too.
Yeah, recreating Bach, probably pretty interesting.
Now, maybe you guys would like to hear a sample of the sound that I have generated. Let me try to play one. If you guys can hear, that's the simple Bach from the default settings, the default hyperparameters. I haven't fiddled with any of the numbers here. I just ran it to see if it runs. So this is the established baseline. It sounds cool. So did you guys hear it?
No, it doesn't play for us.
Okay, just let me try. Yes, okay. So this is the chords.
Yeah, I could hear that.
Yeah.
So this is with respect to default. So these are with respect to the temperature parameters that they have fiddled with 0.8, 1.0, and a 1.5. So, we can play with it, and he has asked us to share his our most beautifully generated photos with him on Twitter too. So
Yeah.
that's a task for us.
If all of us start, or all students start creating these artificially generated pieces, I'm sure at least, like monkeys throwing a dart, somebody is bound to come up with a masterpiece.
Yeah, exactly. And maybe somebody can buy it too. So that was it from my end, guys. Hope you had a good time. And any more queries or anything? Any comments?
No, thank you, Mike. This was hard material to go through.
So we have one more session for this, or
whatever you guys.
Oh, I don't know. I was just wondering, are we looking at code next time or no? I don't know what the schedule is like, Joseph.
Yeah, we've scheduled to move on to 16 with Gautam, but I don't know what people's feeling is. Do you think it would be useful to spend a session just looking at the code and maybe trying some of the exercises? Or we haven't done this in the past, which is probably, but that's only because I wanted to get finished, in March. It's extremely long. We started in August. And if we did this properly, we would have an extra session for looking at the code and the homework every time for every chapter. And that would make it even longer, and some of these may take 2 sessions to look over the homework. So What are people's feelings? Should we have an extra session, or should we just move into chapter 16?
I think so. We can take a look at it at our own personal time too, and discuss at the start of next session if we had any queries, or we can ask those queries in the channel too.
Okay, let's do it that way.
Because it shouldn't prolong, and that's my view. I'm open to other interpretations too.
Okay, let's do that. Let's take care of discussion on the channel and spend a little time at the beginning of next meeting discussing anything about the code that we want to discuss. Okay, well, thank you so much, Mayank. Again, great job just getting through all this complex material. I thought personally that Jérôme did a better job introducing the RNN and its variants than anybody I've ever seen. I mean, it's nice to see that blog from Jay Alamar, but I think Jérôme's high-level descriptions of what these things do, particularly on page, the description of what the LSTM does on, I think it was on page 516, or right under figure 15.9 if you're working out of the online book. I thought it was just a really excellent and very logical summary. Like, you can see from the top down what's going on, and nobody else explained it that way. Anyway, that's just my feeling. Yeah, so once again, thank you, and we'll see everybody.